Okay, so today's announcements are the Chapter 17 sapling is due 9 a.m. Monday next week. And also we have quiz number 2 coming up next week, so that's going to cover everything up through the end of lecture today. So probably like 5 or 6-ish pages into Chapter 18. Okay, any questions about that? Yeah? Mm-hmm. Mm-hmm. Yeah. Yeah, so like emphasis is going to be on the things that have not been asked about yet. So, Okay. Alrighty, so where we left off last time, we're into Chapter 18 now. Hopefully those of you who prefer to use the type chapter notes have gotten a copy of those now that they're posted online. We got most of the way through nucleophilic aromatic substitution. So SNAR is what we're looking at now. So for those of you who missed lecture last time, it's sort of analogous to electrophilic aromatic substitution, except everything is flipped more or less. So instead of a positive charge, it's a negative charge on the ring, and then everything else sort of works out as a consequence of that. So we need to stabilize a negative charge on the ring during the reaction. And so that means that electron withdrawing groups are doing the total opposite of what they did during a couple chapters ago when we were doing EAS. Electron withdrawing groups are actually activating so they actually help pull out some of the extra negative charge on the ring and stabilize the intermediate. So we can look at relative rates. So I guess one thing that's worth pointing out is just like in electrophilic aromatic substitution, whatever groups we have on the ring are going to have the strongest effect when they're ortho-para to the new group. So we can look at relative rates. If we're doing something like this where we have nitro groups ortho and para, it's going to be about 10 to the 5 to 10 to the 6 times as fast as if we have just para. I don't actually have the numbers for meta. My guess is it's quite a bit lower than just para. But I do have the numbers for unsubstituted benzene, which is about 0. So I guess take-home message here is being able to kick the negative charge out onto the nitro groups like we saw the resonance forms for last time makes a huge difference in terms of stabilizing that minus charge. And in fact, if you can't do that, then you're stuck with a minus charge on carbon in all of your resonance forms. If you're having a hard time seeing that, that might be a good practice problem, is show the resonance forms of this thing, trying and failing to do SNAR, because all of them kind of suck. They all have a negative charge on carbon. So this is actually interesting because when we were doing EAS, straight up benzene could still do all of those reactions just fine. It might not have been as fast as an activated ring, but it still did them. When I say these reactions, I mean all of the EAS reactions, so like Friedel-Crafts, nitration, all that. It just wasn't as fast as the activated, which in this context we mean like groups with electron donating potential on them. Here, on the other hand, in SNAR, not having what's an activating group in this context is actually a total deal breaker. Like if you try to do this on an unsubstituted ring other than the leaving group, it just will not work. So you need at least one electron withdrawing group. I don't know if a meta-positioned electron withdrawing group is going to work. I guess for the purposes of our exam, let's assume that's so slow that it would also be no reaction. Let me write that up here. So we'll assume meta-nitro is going to be about the same as benzene, because if you go through the resonance forms, there's no way you can push the negative charge out onto a meta-nitro group, so it's not really helping you at all. Okay. So, one last thing that we do want to look at here is sort of another comparison between the old SN1, SN2 stuff and SNAR, and that is in terms of leaving group ability. Okay, so when we looked at SN1, SN2 before, how good was fluorine as a leaving group? Yeah, I see people shaking their heads. It's not. It's the worst of the leaving groups. Out of all the halogens, at least. And that's because even though it is nice and electronegative, it's not as big as the other halogens, and so when you kick out F minus, it's a stronger base. Than any of the others, Br minus, Cl minus, or I minus. All right, so it's a little bit less stable on its own. Like, it's still not a strong base, but it's not as good holding its negative charge as the other three are. But it turns out leaving group ability is actually not the important aspect of what fluorine is doing in this reaction. Because if you remember the mechanism, which I can draw back up in a second here, by the time the leaving group gets kicked out of the ring, the rate has already been set. So the rate determining step is actually formation of the carbanion. And so the more you can stabilize the carbanion, the faster that's going to go. Turns out, having the fluorine on the ring is actually going to be more stabilizing because it's more electronegative. So to draw that up here, all right. So I'm not going to draw like the first step of the mechanism, but let's say we're skipping ahead a little bit and going to the part where we've already gone to the second step of the mechanism. We have the nucleophile added on here. We have a negative charge. This, the fluorine is going to pull charge out of the ring towards itself because it's fairly electronegative. And that's going to end up stabilizing the negative charge just a little bit more than if we have, say, an iodine as the opposite extreme. That only has, let me actually redraw this even bigger because the carbon-fluorine bond is got a fairly strong dipole on it. Fluorine's very electronegative, whereas carbon-iodine only has a little bit of a dipole. And so that negative charge is not as stabilized. So this forms slower. So yes, even though the last step of the mechanism for these two things is going to be harder for fluorine because booting this guy out on its own is harder than booting out the iodine, doesn't matter because the only thing that controls the rate in this thing is how good is the carbanion in the meantime. Okay, so questions about that? Yeah?
Can you alter the rates, the relative rates of those two by changing temperature?
Yeah, so I don't know if this would be still considered like a decent reaction. My guess is, yeah, you could still show the product for this forming, but you'd probably have to wait a while or heat it up a bunch. Yeah, so I guess, all right, so the non-majors labs don't actually do this, but for the majors chemistry lab, we actually have a microwave reactor that's really cool, and we have the majors actually do this reaction on something that I think has a chlorine on it to start out, so you can actually sort of like heat it up in small pockets at a time and sort of get localized spot heating that actually forces it to go even though it's not a fluorine on there. Yep. Okay. So yeah. Mm-hmm.
I understand that the fluorine is pulling away electron density, but if it has like a partial negative on it, then isn't it also that like two negatives next to each other?
So the fluorine is going to be like delta negative, yep, but the carbon's going to be delta positive as a result, which is closer to the negative charge, so that helps stabilize it. Whereas here you've got like, I'm going to draw it real teeny, so it's probably going to look like a dot from the audience, but it's kind of the same thing, just smaller. Yeah. Okay, so yeah.
Just to confirm, there's no difference in rate between the leaving groups?
So it's actually like the inverse of leaving group ability is because, so this is faster and this is slower, which is the opposite of what we would always have expected for SN1, SN2. Mm-hmm. Yeah, so it's just kind of a consequence of, in this reaction, we add a group first and that gives us a minus charge and everything else kind of pans out from there. So, okay. So other questions about this one? Alrighty, so that wraps it up for regular organic chemistry for this chapter. At this point, we're going to like veer way off sideways into something that is going to take up the rest of this chapter, which is actually a little bit more similar to inorganic chemistry than organic chemistry, but it turns out to be so useful for synthesis that we're going to dip into it a little bit here just so we can understand a couple of reactions that are super important. Okay, so before we do that, we got to look at transition metals. All right, so there's been a few reactions we've seen that involve transition metals before, where I'm always like, don't worry about it, we'll cover it in the future. Now is the time. Okay. So transition metals is everything located in the D block of the periodic table. And I guess, yeah, we got a couple periodic tables in here. But just to sort of draw up what we're looking at. Okay, so we know that in the periodic table, the first two columns are the S blocks. So like those are providing sort of the first two valence electrons for these metals. And so the D block starts at 3 valence electrons and we go across from there. Okay. So I probably won't draw in the whole thing actually, but this is kind of what we're looking at. Like scandium starts at 3 valence electrons, then titanium, vanadium, and chromium, and eventually we get over here to zinc, which has 12 valence electrons. Okay, so electron counting for these things. I guess if you guys remember that when we were learning like Lewis dot structures way back in OChem or even in Gen Chem before that, we had sort of a couple different ways of counting electrons. We could count for an octet, which is where we want to optimize for a total of 8 electrons, or we could count a different way where we're counting for formal charge, and there we want to have sort of a number of electrons that matches what it should be for the neutral atom. So we're actually going to have several different methods of electron counting here too, where we're trying to optimize all of them at once for a certain number. Actually, before we get into that though, we're going to look at bonding to transition metals, which is also a little bit different than just covalent bonding. So rather than covalent or ionic bonds, we're going to see usually the groups that stick to the transition metal are called ligands. And they donate electrons to the metal's octet in a couple different ways. Okay, so ligands just means something that's tied to or something that's bonded to. Okay. So L-types their whole deal is that they show up and just straight away donate 2 electrons to the metal. So when they're floating around by themselves, they're neutral on their own. Okay. So these are going to be donating 2 electrons directly to the metal. In what's called a dative bond, so usually covalent bonds we're used to seeing like each atom contributes 1 electron to the bond. Here, both of them are coming from the same ligand. So it's a little bit different from covalent bonding. And dative bonds are actually usually shown as, instead of like a line between atoms, they're shown as an arrow pointing at the metal. So they can be shown as a line actually, but they could be shown as an arrow. So I guess be aware that either one might show up. Okay, so let me kind of show how that looks here. So here's a platinum with a couple of chlorines attached to it. That's the other type of ligand, which we'll cover in a second here. But if we have, say, an ammonia molecule here, NH3 with a lone pair, it can actually contribute its lone pair and throw both of those electrons at the metal. And so we would show it as just this permanent complex with a lone pair pointing at the metal from the L-type ligand, this NH3. So either one of these could dissociate. In other words, if it falls off the metal atom and breaks that dative bond, both NH3 and the metal, platinum in this case, are neutral afterwards. So we could draw the same thing afterwards. Maybe one of them stays on, and then the other is just floating around with its lone pairs, kind of unclaimed at that point. Okay, so most common things that are going to show up in the L-type category are anything with a lone pair that's neutral usually. There we go. So many neutral molecules with lone pairs. So for example, NH3, H2O, carbon monoxide, as it turns out, actually shows up a ton in this chapter. So that actually looks like, if you figure out the Lewis dot structure for carbon monoxide, the best way to show it is a triple bond here with lone pairs on both the carbon and the oxygen, because that's the only way to get a full octet on everyone. And that puts you at a negative charge here, positive charge here. And so usually that's going to be associated to the metal by its carbon end, because that's kind of the most electron-rich part. And then one that we're going to see a ton of that's really common for transition metals is something that's kind of analogous to an amine, so like nitrogen with 3 R groups coming off of it. Actually, I guess I can list an amine here as well. It's not in the notes, but that's possible too. But one that we're going to see a ton of is basically the same as an amine, just instead of nitrogen, we're going 1 down in the periodic table, so phosphorus with 3 R groups. Okay, so phosphine ligands. Also have a lone pair to contribute here. Okay, so that's one category of things that we're going to see that can do this. The other is anything with a pi bond can do this. So alkenes and also aromatic rings. And aromatic rings can actually donate from all 3 of their pi bonds at once. Which means that aromatic rings can actually act as like 3 L-type ligands at once. So we would call these L3 ligands. Okay, so that might look like, oh, I guess I haven't explicitly said this, but a lot of the time we'll use a capital M to just abbreviate as like some transition metal. We're not specifying what. But again, we can have, oh, sorry. Yeah.
So with the data bonds, we don't show like formal charges?
Correct, yeah. So transition metals are a little bit weird as far as formal charges. We'll get more into that once we start looking at different methods of electron counting, though. So,
Are data bonds different from ionic bonds?
So good question. I guess like I might table that for a little bit, and then we can start counting electrons and like see how the differences work out, I guess. But yeah, to some extent they are ionic bonds. It's just not as polarized as they might be for like 2 things that are not transition metals. So, okay. So if we're looking at, say, an alkene here, we could show an arrow like coming straight out of the pi bond and going towards the metal, and those electrons would be contributing some density onto the metal. Or we could do something that, all right, I'm going to draw a benzene ring sort of edge on here. And this thing can contribute all 3 of its pi bonds at once onto the metal. So this is kind of acting as like 3 L-type ligands at the same time. Okay. So the other type of ligand that we're going to look at is X-type. And these become anions when they are removed from the metal. Okay, so if you break the, actually, I guess another way to phrase this, and if they're on their own, the metal has to take on a positive charge when they leave. Okay, so this is a little bit more like what we're used to seeing for covalent bonds. It's like, again, this platinum thing that I drew up before. If we break off one of the chlorines, we're going to get Cl minus, and then the platinum has a plus charge as a result. Okay, so we can actually have things that act as like L-type and X-type at the same time. So benzene is an L3 ligand. It's acting like 3 L-type ligands. This one is probably relevant to everyone who's taking lab right now. This thing, cyclopentadienyl, it's got 2 pi bonds, so it's sort of a double L-type, and it's also got this negative charged anion here. So this one is what's called an L2X, because it's got 2 L-type and a negative charge. So overall, if we did, for instance, an iron atom here, it's contributing from both of its pi bonds at once in dative bonds, and it's also doing like an X-type bond from the negative charge onto the iron. Mm-hmm. Yeah, so usually we only show the arrow for the dative bonds for L-type ligands. The X-type we show as a regular line bond. But some sources will also show dative bonds as lines, unfortunately, so sometimes you can't tell them apart like necessarily, and so then you have to figure out like, if I split this group off, is it going to be neutral or is it going to take a negative charge based on what I know of having a full octet, that sort of thing. Okay. So now what we're going to look at is counting electrons on the transition metal and how that varies depending on what ligands we got attached. Okay, so three ways to count the electrons on the metal. 2 of them are actually pretty identical to what we're used to seeing on carbon, just with slightly different limits. We're no longer constrained by the octet rule. Instead, we have what's called an 18 electron rule, and then one of them is kind of different. Okay, so oxidation state is pretty much the same as formal charges from before. So bonds to X-type ligands are counted the same as like covalent bonds. So one electron goes to the metal, one electron goes to the X-type ligand. L-type ligands have both electrons counted towards the ligand. Okay, so what this works out to be, since the electrons from the L-type ligand end up not actually affecting the oxidation state of the metal at all, because they're not actually putting a charge on the metal if they leave. Basically, we can work this out to be, move this down. So the oxidation state on the metal atom is number of X-type ligands plus whatever charge is written on the metal. Okay, so in the notes I pretty much run through all three of the counting methods before doing an example, but I think I'm going to intersperse like working through this first example that I have in the notes just because that might make it clearer as we go along. And actually the first example is the one that I've been drawing up here so far. So platinum with 2 chlorines and 2 NH3s on it. Its oxidation state is going to be the number of X-type ligands on the metal. So 2 plus 0 because there's no charge written on the metal. We will see some examples where you might have like platinum with a plus charge and some ligands going on, and then you would have some number here. But the oxidation state here is just going to be 2. Okay. So usually whatever oxidation state we have is written in Roman numerals. So this particular complex has platinum 2 oxidation state. Okay. I think we looked real briefly at this during like the oxidation of alcohols thing back in OChem 1, but that's kind of where this is coming from. Okay. All right, so questions about that example so far? Yeah. Yeah, because the X-type, it turns out, affect the charge on the metal if they're gone. Like, if we pulled both of these chlorines off of here, we'd have platinum plus 2. But if we pulled the nitrogens off, that wouldn't change anything. So that's kind of where it's coming from. Like, if we rip all the ligands off this guy, what total charge are we going to get on the metal? Okay. So the next wave, oh yeah, question.
Will the metal ever have a negative charge?
Very rarely, because usually it's less electronegative than most of the stuff that could end up bonded to it, but it is possible, like sometimes, I guess. So, yeah, but almost always it's going to be positive charge. I don't even know how you'd write it for the Roman numerals for the oxidation state if it's negative. I guess maybe like -2? I don't know. I haven't seen it, but I'm guessing that's how you do it. If it's a 0, which we will see occasionally, so like we could see some complexes that are like iron 0. That's something that does come up sometimes. I guess there's no Roman numeral for 0. But that's kind of another thing you might see.
Have you ever had a situation where the formal charge on the platinum, if you like negative, but based off the way the oxidation states could be something along the lines of 2 plus negative 1 or something like that.
Oh yeah, you totally could get that. So like if we had platinum with a minus charge, so that would be -1, and then your oxidation state would be 2 plus -1 gives you an oxidation state of 1. So yeah, that could show up, just not in this particular case. Yep. Okay. So this is pretty analogous to the formal oxidation state. Just we have more complicated ways of counting electrons because there's now 2 different ways they could be contributed to the metal. This one is a little bit different. This is unshared electrons. This is sort of analogous to counting how many lone pairs there are on the metal. Whether you actually count them as lone pairs or not is a little bit iffy. I guess like the mechanisms where we've used transition metals before, like oxymercuration, we just showed a lone pair on mercury. Debatable, but there's still like unshared electrons on the metal is what we're looking at here. So this is described in what's called D superscript N notation. So the N on there is just how many electrons are unshared on the metal. So this we can calculate kind of like we did for, carbon or whoever, like oxygen or nitrogen. We need to know the number of default valence electrons on the metal from the periodic table and the oxidation state. So N is going to be number of valence electrons in the neutral metal minus the oxidation state. And if you want to like calculate N from scratch, you can pretty much plug in like the whole formula for oxidation state into here if you want, but usually you're sort of running through all 3 of these at once, and so you've already figured out the oxidation state by the time you get to this point. Okay, so again, assuming we're using this platinum thing as our example, platinum with 2 chlorines, 2 nitrogens. Platinum itself has 10 electrons because it's under nickel. So N here for this particular compound is going to be 10 minus 2. So 8 unshared electrons on the platinum. So in other words, platinum is D8 is how we would describe that. Okay. Questions about that one?
This is just another method of counting the d electrons, essentially.
Yeah, so it's sort of like how many electrons are left to the metal once you deal with the fact that some of them might be tied up in bonding to X-type ligands and not really belonging to the metal anymore at that particular moment. Okay, so the last one we're going to look at is electron count. And this is the closest analogy to the octet rule. But because we're not just dealing with an s and 3p orbitals, we're actually dealing with so instead of just 4 orbitals or 8 electrons to fill, we actually have access to d orbitals. So we have 1s 3p, and 5d orbitals. So that's 9 orbitals total, so we have room for 18 electrons. Lower down in the periodic table, we can theoretically actually start violating that by using the f orbitals, kind of like we can violate the octet rule and start using d orbitals. But we're going to be sticking to the 18 electron limit here. But we can also have unfilled 18 electron sets. There's going to be plenty of times we'll see things that are fewer than 18 electrons. Okay, so this is going to be electron count is number of valence electrons. So in neutral metal minus the charge plus the number of X-type plus 2 times number of L-type, because we're really only getting 1 electron contributed from the X-type to form that bond, but the L-type is showing up with 2 electrons that it's contributing all on its own. Okay, and you can sort of rearrange that to plug in parts that you know from the previous 2 formulas if you want. But that's kind of where we're coming from. And as a heads up, these formulas, if I want you to calculate anything for those on the exam, I'm going to provide those formulas. So you don't have to memorize them. I'd rather have you sort of know how to apply them, I guess. Okay, so again, platinum here. This thing has an electron count. It's going to be 10 electrons in the neutral metal minus 0 charge plus 2 electrons from the number of X-type ligands plus 2 electrons from each of the 2 L-type ligands. So 10 plus 2 is 12, plus 4 is 16 electrons. So this particular one could actually squeeze a couple more electrons in there. Maybe we could have like another NH3 ligand associate on there, and then we would be at the full complete set of 18. Or we could do some other stuff on there to change it. Okay. So, I guess maybe let's do one more example where we apply all 3 of these. Okay, so I don't know if I have time to draw out the whole thing, but in the notes, it's kind of cool looking. Okay, so this is actually relevant because okay, so okay, I kind of don't want to draw out the whole thing, but maybe I have to. Okay, I'm going to leave it real vague. There's this polycyclic structure with multiple aromatic rings kind of connected together. This is actually the structure of heme. This is what sort of binds to the iron and keeps it in the red blood cells in your body. But heme itself, if you have it neutral, it's got 2 nitrogens on opposite corners with lone pairs, and then 2 that, if left on their own, would be negative charged. So when it binds to iron, you end up forming 2 dative bonds from the lone pairs and 2 regular covalent bonds from the X-type negative charged nitrogens. And then You can also show this. This is kind of where different ligands can come and bind to the remaining space on the iron, depending on if you've got like oxygen or if you've got carbon monoxide going on or something like that. I'm just going to show water on here. So that can form dative bonds. Let's show it sort of on the top and the bottom. I'm gonna do it in time. Okay, so I got 1 more minute. Okay, so here the oxidation state. Iron is shown with no formal charge on it, so it's neutral, but we got 2 X-type ligands on it. So the oxidation state is 2, or iron Roman numeral 2. Unshared electrons here is going to be 8 for neutral iron, minus 2 for the oxidation state is 6. Or in other words, we were to write this as D6. And then electron count here is going to be 8 for the neutral metal, minus 0 for the charge, plus 2 for the X-type, plus 2 times all of 4 different L-type ligands on there is going to be a full set of 18 right now. Okay, so a lot of this is kind of analogous to what we saw in just straight organic chemistry, but the inorganic chemists have sort of gotten their own conventions developed that are going to be a little bit different from what you're used to seeing.